this is Unit 1, Day 4, Continuity. Again, this is a technical format. You got to have it right. It's not enough to just sort of understand it. You have to be able to say it and say it correctly. I say all that. There's sort of two aspects of this lesson. The first part is makes sense. It's just, can you think about it, figure it out? That's no big deal. It's the second part that gets a little bit technical. But before we get there, continuity is a big deal because it's a criteria for several definitions and theorems. We don't care what those definitions and theorems are yet, but quite a few definitions or theorems in calculus start with, if f of x is continuous, then blah blah blah, some other calculus thing. And on a free response part of the AP test, if you want to use that, you have to prove that it's continuous. So you can't just say, oh, it's continuous, therefore I can make this conclusion. Like, you have to show that it's continuous. So you've got to understand the proper technique for showing continuity. And this is why it's important. It's because we keep using it. Limits, they're important, but we don't keep using them. They're not the foundation of everything. Well, in some ways they are, but you don't have to keep showing them. Continuity you do. So we got to make sure we understand it well. Haven't come up with a good title for Roman numeral 1 and Roman numeral 2. Roman numeral 2 is going to be like the technical definition. So there's Roman numeral 2. Roman numeral 1, intuitive continuity. Just made that up. You won't find that phrase in a calculus book. But I think this first section is like, yeah, that just makes sense. I can figure that out. That graph's continuous, that graph's not. I don't even know that you need a definition, but can you draw the graph without lifting your pencil? Can you draw the graph without lifting your pencil? So no jumps, no holes, no asymptotes, nothing crazy. Well, I say no asymptotes. You could have an asymptote at the end. So let's draw something that is continuous. And by the way, if you're planning ahead, we're going to put 4 graphs across here, so don't make this first one too big. So nice and smooth, nothing crazy. I mean, I guess that's a crazy graph, but it's continuous. I was able to draw it without lifting my pencil. So now let's start drawing graphs that are not continuous. Let's put a hole in one here. And your graph doesn't really need to look exactly like mine. It just needs to have a hole in it somewhere. And in fact, we'll say it has a hole at A, at x equals A. So we would say f of x has a point discontinuity at x equals A. So we have to be careful. We would say the graph is not continuous, but it would be better to say it's not continuous at x equals A. Because later on, if we want to do something with, the part of the graph over here, well, it is continuous over there. And so all those theorems that require continuity, if we If we don't have the whole, then we'd be okay to use them. So be careful when you say it's not continuous. You're correct, that graph is not continuous, but it's better to say that it's not continuous at A, meaning it is continuous everywhere else. Point discontinuity, that's fancy talk for a hole. Let's give this one a vertical asymptote, the next one. Again, I think you can just tell by looking, that's not continuous. I can't draw that graph without lifting my pencil because there's two different branches. For this one, we would say f of x has an infinite discontinuity. At x equals a. And again, it's kind of a new term for an old topic. That's the same thing as a vertical asymptote. I know how to spell asymptote. Asymptote. Just like point discontinuity as a whole. So those are maybe new words for things we already know about. So point discontinuity is a whole. Infinite discontinuity is a vertical asymptote. And kind of the same thing. This is continuous other places. So if we're asked a calculus question about x equals -3, well, that's fine. It is continuous there. So be careful about continuity. Lastly is a jump discontinuity. Something like that. Jump discontinuity at x equals a. And that one doesn't get a special name because it's a jump. We already, like these other two, have two names. Point discontinuity is a whole. Infinite discontinuity is a vertical asymptote. A jump discontinuity is a jump, so it doesn't get an extra name attached to it. So those are sort of the three only types of discontinuity. Holes, vertical asymptotes, and jumps. That's sort of the intuitive continuity. Like you just look at those, and probably in middle school I could have just said, is that graph continuous? And even without a formal definition, you probably would have said, well, no, there's a jump there. You wouldn't have said jump, but maybe you would have. Like, it's not continuous, those three. So part of continuity is, I think, obvious. Like, yeah, those aren't continuous. That one is. Leave just a little bit of space because we're going to come back and put some more notes on there, but not very much. So like I'm leaving maybe one line or two lines there to come back to that in a moment. Roman numeral 2 is the technical definition of continuity. And this is important. A lot of times in math, we give you these definitions and we say, you don't have to really know the definition, you just have to be able to use it or recognize it. That is not the case here. Like you're going to have to use this and use it in the right format. F of x is continuous at x equals a if and only if, there's like geometry definition statement in there that you haven't seen in forever. If and only if means it's a definition, means it's bidirectional, meaning if it's continuous, then this thing is true, and if this thing is true, then it's continuous. Now, what this thing is a three-step equation. So you'll need to know this and show this if I ask you to show continuity. The limit as x approaches a from the left equals the limit as x approaches a from the right There's one more part of this, but let's pause there for a second. So which one of those pictures is the limit from the left not equal to the limit from the right? First, second, third, or fourth? Are the left and right limits different? Fourth. Okay. On the second one, the left limit and the right limit are the same. Right? We're okay so far. So that's why we need another part of this statement, because B is not continuous, but that graph B does fit this criteria. So I need one more piece, and that says that those two limits have to equal the function value there. Again, if I ask you to show or prove continuity, I want to see those three things. And so you'll start by writing those three things, and then you'll start working, and then either they all equal each other, or you'll figure out somewhere that doesn't work, and then you can say it's not continuous there. But you've got to know that. Okay, let's see. Go back up to the top and add a few notes, because there's two types of continuity. Or two types of discontinuity, I guess I should say. That first type, the whole, we call that a removable discontinuity. Any guesses on why we call it a removable discontinuity? You could phrase it a couple ways. You could say someone removed a piece of the line. But I want to remove the discontinuity. So if I remove, how could I remove the discontinuity? Fill in the hole. Another way to say it, unofficial, not a formal word, but it's a fixable discontinuity. I can fix that. Fill in the hole, and it's no longer discontinuous. So it's like it's almost continuous. I can fix the discontinuity. The other two aren't fixable. So we say those are non-removable discontinuities. I mean, if you could fix them, you'd have to totally rearrange the equation. Like to get rid of a vertical asymptote, that would take some major doing and change the equation significantly. To fix this jump, you'd have to rework something pretty big. To fill a hole, that's a pretty easy thing to do. So we have a removable discontinuity and we have non-removable discontinuity. Fixable discontinuities, not fixable discontinuities. Obviously, we kind of prefer the removable ones because you can fix them, and then you can work with whatever you need to work with. All right, let's do an example here, or several examples. Where is it discontinuous? And I'm going to give you an equation. discontinuous. So let's say f of x equals x plus 2, x minus 3 over x plus 2. So I want to do this sort of two ways, the intuitive way, but then also the formal way, because I need you to be able to do it both ways. So like the way this question is worded, you don't need to do the formal way because it didn't say prove or show. It just says where's it discontinuous. So you tell me, looking at that equation, where is it not continuous? Where's the problem? Or is there a problem? What's that? Where's the hole? So there's a hole at x equals negative 2. So not continuous at x equals negative 2. That's sort of the type 1 answer, the intuitive answer, the not very formal answer. Intuitive answer. And again, that depending on the question, that might be fine. But let's also look at the technical definition and see if we can figure out how this breaks down on the technical side. So yes, there's a hole there. But if I ask you to show where this thing is discontinuous or prove that it's discontinuous somewhere, I want you to think that and know that, but I want to see this sort of three-sided equation here. And so I would just start by writing the three-sided equation, and then we'll figure out where it breaks down. So there's our formal definition of continuity. So now we already know it's a hole, so we can use that. Does the limit from the left equal the limit from the right? Yeah. Does it equal the function value? No. So you could put not equal there because there's a hole. And so it's sort of, it's the same reason, it's just using the technical definition. There's a hole there, so the function isn't defined there, so therefore this is not continuous at x equals negative 2. Again, it kind of depends on the problem whether this sort of intuitive answer is okay or whether I want a technical answer. The technical answer is always okay. I guess I could phrase it this way. You can always do that, and if you're stuck, maybe you should do that. If you can't figure out what's going on, at least start with that. That'd probably get you some partial credit and might lead you to the answer. Second example. G of x equals piecewise function incoming here. X squared plus 3 when x is greater than or equal to 1. 5x minus 7 when x is less than 1. So, continuous or not continuous. Any ideas on where it might not be continuous? I feel like there's only one spot where it might not work.
1.
Yeah, at 1, there might be a jump going on here. So, like individually, both of those pieces are continuous. Right? Because x squared and 5x minus, those are continuous. Those are polynomials. Those are nothing weird with those. But something might be going on at x equals 1. And something might be going on, meaning we might have that situation. So how do I test for that situation?
You put 1 into both equations and see if they have the same output.
Perfect. We'll put one into part A, and we'll put one into part B, and we'll see if they're the same. Now, that might feel a little strange, and maybe it should feel a little strange to put one into part B, because we're only supposed to put it into plugging in things that are less than 1. But if we're talking limits, we are plugging in something less than 1. We're plugging in 0.999999999, which is pretty close to 1. So we're going to plug it into A and plug it into B and see what we get. Let's use the official words here. So that what we're doing is the limit as x approaches 1 from the left so that would be part B, because if we're a little less than 1, we're on part B. So that would be -2. And then the limit as x approaches 1 from the right, that would put us on part A, because we're plugging in 1.000000001. And we get 4. So what does that mean? So it's not continuous or discontinuous. But let's be more specific, not continuous at x equals 1. And by the way, we sort of did the technical version on that, right? Because we just showed that the two limits, the left limit doesn't equal the right limit, so it's not continuous. So that is the technical definition there. We didn't even need to worry about f of 1 because it doesn't matter. It doesn't work. Here's a fun continuity question that comes up frequently on my test and the AP test. Find the value of k that makes g of x continuous another piecewise equation. Find the value of k that makes g of x continuous, where g of x is x squared plus 3 when x is greater than or equal to 1, kx minus 7 when x is less than 1. Probably did those two examples 2 or 3 years before I realized, wait a minute, number 2 and number 3 are related examples, right? Look at the equation, x squared plus 3, 5x minus 7. That was not continuous. That's what we just showed. At 1, that didn't work. Now we're going to switch things up. So instead of 5x minus 7, we got kx minus 7, but we want to figure out what k is to make those match. So instead of having a jump, we want them to tie together at x equals 1. So what should I do to sort of force them to tie together at x equals 1?
Set them equal to each other?
So kind of what we did on the last one, plug it into both, but this time we're going to set them equal to each other to force them to be equal. So I'm going to show more work than you probably would. Like officially we want the limit from the left to equal the limit from the right. So the left is part B, the way I lay this out. Right is part A. So k times 1 minus 7. I want that to equal 1 squared plus 3. So k minus 7 equals 4. So k equals 11. So we used that idea of continuity, but we threw a little curveball in there it was the same type thing, same process, a different type of answer. So if k is 11, that forces continuity. See which equations or what examples we can get by without doing. Let's do one more. I think we'll be okay if we do one more. Well, I say one more. It's one of those 3 questions in one. Which of the following? So maybe 3 choices, and it's going to be one of those 1 and 2, 2 and 3, 1 and 3, 1, 2 and 3 type questions. Which of the following is continuous at x equals 1? Statement 1, f of x equals, we do love our piecewise equations in this section because there's lots of continuity issues with piecewise equations, or potential continuity issues, I guess I should say. Kind of a goofy one. X squared minus 2x plus 1 over x minus 1. When x is not equal to 1, and when x is equal to 1, then our output is 1. So that's kind of a weird statement. Roman numeral 2, g of x equals x squared plus x plus 1 over x plus 1. Numeral 3, and I'm writing smaller to try to fit it all on there. H of x is another piecewise function. 1/2 x plus 1 plus 1 when x is less than or equal to 1, and 2 when x is greater than 1. Okay, pause for a second. You got all that down? I have to cover a lot in calculus, but I never want to be the teacher that just races through and so that you have no time to think. All you're doing is frantically copying down, and then you had no time to process anything. Okay, continuous at x equal 1. So number 1, let's see. There's a potential problem here because there's a dot at 1, 1. Right? I know that when x is 1, y is 1, but the rest of that thing, I don't know what's going on there. So, what do you think we could do with this thing? Any thoughts? What can we do with that numerator? Let's factor it. X minus 1 over x minus 1. Oh, this is good. What's going on there? There's a hole. But if we're at x equals 1, we're not really on this graph. Right? This graph has a hole at x equals 1. We want to see if this point fills it in, basically. So what's left is x minus 1. Let's plug in 1 and see where the hole is. So there's a hole at x equals 1. So let's plug that into what's left. 1 minus 1 is 0. So there's a hole at 1, 0. That means that what this graph looks like, I'll hold it 1, 0. So now let's answer the question. Is it continuous at x equals 1? No. I mean, it's easy now because we're looking at a picture. So that one's a no. Okay. Roman numeral 2. The top doesn't factor, so I don't have to worry about that. What's going on at, this is pre-cal question, at x equals negative 1? What's happening? Factors at the bottom that don't cancel? What does that mean for the graph? So factors that cancel make a whole. Factor in the bottom that doesn't cancel, it's a vertical asymptote. So that would definitely not be continuous at negative 1. I don't know what this thing looks like, but there's definitely a vertical asymptote at negative 1. But now reread the question. Which of the following is continuous at x equals 1? So is this graph continuous at x equals 1? I'm going to say yes. At x equals negative 1, it's not continuous. But it is continuous at x equals 1. There's no problem with x equals 1. So that is continuous at x equals 1. So that at x equals 1 is pretty important there. So that graph would have a discontinuity, but it would not be at x equals 1. And then lastly, another piecewise. So we're checking the jump thing here. So we need to plug it into part A and part B and see if they match. So 1/2, 1 plus 1 plus 1. Let's see, half of 2 is 1, 1 plus 1 is 2. For part B, there's nowhere to plug it in. The answer is just 2. And so, yes, that is continuous at x equals 1 because of the left and the right matched. So 2 was just kind of tricky, but 1 and 3, 1 was a hole, 3 was potentially a jump, but not a jump. They made them match up. Rewind, and then we're done. 3 types of discontinuity. We tried to see several examples of each. Hole, vertical asymptote, or jump. So that's the easy way to think of it, and easy to recognize if you're looking at a picture. Things get a little trickier when you get to equations. They still match up, but it's harder because it's just not a picture. The limits have to equal each other. Again, so if those 2 are true, it might be a hole, but if you fill in that last one, it would fill in the hole. If those 2 are not true, then you got, what's happening there if those 2 are not true? If the left and right limits aren't the same, what's that mean for the graph? There it is. Somebody was doing it with their hands. I saw one of these. Yeah, that would be a jump. Headed toward 3, headed toward negative 1, that's a jump. That doesn't work. And an asymptote, in terms of this, an asymptote, one of your limits would be infinity, and you can't say infinity equals infinity. That doesn't work. So if you get infinity in any of these, then it just blows it up. You can't say, well, they're both equal infinity. That doesn't work. So that's where the asymptotes would sort of fit into this technical definition. Yes, no? Questions? All right, your assignment is worksheet next, which I think is worksheet 4. Yes, continuity.